All right then. So, last time we left off on chapter 28, I believe. Slide 20. Everybody there with me? Okay, fantastic. So, this is the DNA ligase. It's going to seal breakdown in the double-stranded DNA. It's going to catalyze the formation of your phosphodiester linkage between the 3' hydroxyl group at the end of one DNA chain and the 5' hydroxyl group at the other end. It cannot link to single-stranded DNA molecules or circularize a single-stranded DNA. The reaction is going to require an energy source. Typically, it's going to be ATP in eukaryotes and archaea, NAD plus in bacteria, actually. So the DNA ligase is going to catalyze the joining of two DNA strands. Does anybody remember how to easily remember ligase and what it does? Okay. Ligate means to join. Okay, so ligase, to join. Okay, so right here again, this is your your base at the end. Again, this is going to be the base we're joining. Notice again, it's this one right here is going to be the one joining, and this is going to be a phosphodiester linkage. Again, this is the NAD plus for the bacteria, and this one is the ATP for the eukaryotes. Right there. Everybody okay with that part? Okay. Everybody's okay with understanding why this is NMN right here? Yeah, we're going to get this NAD plus here going to that. Okay. Okay, so again, that's that phosphodiester linkage. And in eukaryotes, the energy coming from the ATP will go into the AMP is going to be driving this. So the helicases is going to catalyze the separation of two strands of the double helix. This will allow each strand to act as a template. It's going to require, again, ATP. This will consist of a ring-like structure that's composed of 6 subunits. And again, you can think of this a bit like an unzipping of that region. Now, it typically does come back together later into strands on the two sides, okay? So, the AMP-PNP, this is the non-hydrolyzable ATP analog. This is going to be used to elucidate the helicase structure and the function. This is how we can actually detect what the hell is going on in these processes, because we're putting in things that can't actually process and break apart, okay? And this is how we do it. Note that the reason it cannot chop these apart is the nitrogen here. That's a stronger bond than it would be for the oxygen. Okay? Okay. So again, these are the hexamers for the helicases. That's 6 subunits. Each of the subunits is going to have 2 loops. Right there are the 2 loops that extend towards the center of the ring structure, and they're going to interact with that DNA. It interacts closely with its 2 neighbors within the ring structure. And so you can see these loops coming in, see that repeated motif here? It's a little hard to see on some of them, but like here it is for that one. Everybody see that okay? Fantastic. Does anybody know what those kind of look like? Remember our phosphate loops that we looked at a lot before? Look a lot like that, don't they? Because they have similar purposes. So again, there's going to be 2 classes of your nucleotide binding sites. With one that's going to be well suited to binding the ATP but does not catalyze its hydrolysis. The other one is well suited to catalyzing the hydrolysis but does not release the hydrolysis products. Right here we can actually see that AMP-PNP, which is this right here, which can't be hydrolyzed, and we can then see where it sticks. Okay? This would normally be where the ATP sticks, but now we can't hydrolyze it and use it, right? Okay. Does everybody get why the name is like it is? So this is AMP right here, just like the normal AMP. This part right here is P, nitrogen, N, P. So it's exactly what it is, right? Okay. And again, we see that right here, that these are sticking there, and we can actually see the site sticking to the where the ATPs would stick. Okay? So, the mechanism of your helicase, step 1, you're going to have a single strand of DNA. This is going to fit through the ring center. It's going to bind to loops on 2 adjacent subunits. One will be bound to ATP, the other is going to be bound to the ADP plus an orthophosphate. Step 2 is the ATP is going to bind to the domains that initially had no bound nucleotides. This is going to lead to conformational change that can cause the release of your ADP and the orthophosphate from the 2 subunits, and the binding of the single-stranded DNA by one of the domains that just was bound to the ATP. Step 3, the helicase acts as your wedge. This is going to force your 2 strands of the double helix apart. When I said that this is like a zipper, it actually is a pretty good approximation for a zipper, but has anybody ever seen a shuttle for weaving? Okay, so like when you're weaving rope things, you can have these shuttle things that move through the rope, and they twist as they're unzipping it. That actually is a great mental picture if you know what that looks like. If you don't know what that looks like, it doesn't help you at all, right? Think of a zipper, but instead of just going vertically, it twists while it's going through. Okay? But it works very much like a zipper. Okay? It physically separates the units, and then they can come apart back together later if you don't have something to block you from coming back together. Okay? Okay, so again, this is going to force the 2 strands of the double helix apart. Step 4 is then the cycle repeats, moving 2 bases along the DNA strand each time. Think of this again, very, very similar to our ATP synthase. Okay? Except instead of moving it with H pluses powering that movement and then putting together the ATPs, we're instead driving it the reverse, and we're actually separating stuff as we move along. Okay? Does that make sense to you? Okay, so this is actually the helicases. They're unwinding our DNA here. So again, we have this strand right here that's going to feed through. The other strand is going to get separated and move off. Can everybody see that okay? Okay, and so what we're going to do is we're going to bind and then move like little ratchets on a bike chain. Is that making sense? Okay. And each time the ratcheting happens, you're going to have 2 of the ratchets stuck in. Okay? And that's what you're seeing here. Everybody say that okay? Okay. And that's what we're doing. A lot like a bike chain, right? Okay. Yep. And here's our ATPs coming in. We're going to have exchange of 2 ATP, moving this along 2 each time. And again, this is that ATP, ADP right there. And then we're bound to those sites. Here we have an exchange that's going to happen where we're exchanging along. And so this yellow one ends up going to the ADP. This blue one here is going to go to the ATP right there. And then we're going to get exchanges here. Everybody see that okay? So the DNA in the front of the helicase is going to become overwound in the absence of other changes. Anybody ever tried to lay out a long length of hose or wiring? Okay. What happens as you're unwinding it? Yeah, it kind of starts pushing against you, right? And then it like start winding itself and creating knots, right? And that's that super winding. We kind of have touched on it before with the DNA, but now we're going to look at it a bit more. And so that's actually what's happening. It's becoming overwound as you're unwinding it because that pressure, part of the energy is going back in, right? Okay. And so supercoiling, this is the process by which the DNA double helices that are torsionally stressed are going to fold up on themselves. That's actually what that process is called if you were to be laying down cable or if you're going to be doing a hose. That's also supercoiling. Okay? It always was, just nobody ever uses that word, except for biochemistry. Hi. I know. So again, that's that torsional strain, that torsional stress folding up on itself. This is going to form tertiary structures if nothing's done about it. It will make the DNA more compact as well, kind of like if you ever look at a wiring inside of a wire. It has the coiling of the wires around each other, right? But then it has the coiling you do for the cable, where you coil it around your arm or some sort of surface. Yeah. Same thing. And again, you do the same thing because it makes it more compact. If you had just had those loose wires everywhere, that would have been a hell of an issue, right? Okay. So the supercoiled DNA, this is going to move faster than the relaxed DNA when you do things like analyze it by centrifuge or electrophoresis. Because if it's all loose, right, it's going to get tangled and it's going to act a bit like starch, isn't it? Where it's going to resist change, resist flow. Okay? So the topoisomerase, this is going to be the enzymes that's going to directly alter your DNA winding and supercoiling. Is everybody okay with the naming there and how it relates? Topography, topo, iso, changes in your topography, right? Okay. So topoisomerases. Okay, so this is actually what we're exactly looking at. Can you guys even see that? Yes? Okay. Actually try this. Better? Oops. All right. So there's a few different numbers we have to keep track of and understand when we are looking at DNA structures. And these are the linking number, LK, the twist number, TW, the Rith number, WR. And again, these are going to be for that circular DNA, and these will actually be related to each other. Because just like when you're looking at cabling or hosing, you're going to have that same thing. The more you twist it up around your arm, the more it's going to try to supercoil, right? Unless you do something to that supercoil. Okay? So, I know. You actually kind of intuitively know this, don't you? Which is nice. So again, this is going to be some of the different structures. Right here, we have those linkages right here. This is going to be the 1, 5, 10, 15, 20, 25. And we can see that right there. This actually is related to then this linked circle or relaxed circle right here. And so this would just be this joined back onto itself in a circular form, right? This one being the straight chain. And so our link number is 25, our twist number is 25, and our Rith is 0 in this case. So what if we take that DNA right here and we go ahead and untwist it a couple coils? So we go from 25 to 23. See that? So we untwist a bit of it. Kind of like you would do for wiring, right? I need to untwist some, so I got some loose ends to work with. Okay? Okay, so this would be the, again, unwound circle. And again, we have the 1 to 23. And this is going to be our link. And our twist are both going to be 23. Because again, we don't have any other more complex structures in there. It's just one circle, no other supercoiling going on. Okay? Like if you laid down the hose really carefully on the ground to make a big circle. Yeah. There's no real difference between it being straight and circled, right? It doesn't supercoil anymore, it doesn't twist on you, it doesn't do anything. Okay? Okay, so this is actually going to be a negative superhelix. And what we're seeing here is that we were twisting it the left-handed twist. You see that? Okay. And it's coming around on itself like this. Okay. And so what we've done here is we've supercoiled or superhelixed it the opposite direction here. Okay? And what we see here is, again, our link numbers, they're the exact same. Can everybody see that okay? And that's because these are the linked numbers right here. It's just a straight up twisting of the individual chain. Now, our twists, we have 2 extra twists, don't we? Okay? And so that's 25. And again, those extra twists are in that same twisting there. Our width number actually is -2, though. And that's because we have done it the opposite direction of our other rotations. Is that making sense? Okay. And the width number is always counted by the number of times the DNA double strand crosses itself. Okay? That'll really help you out in counting it. And so we look here, it crosses itself 1, 2. Okay? Notice it's not the circles. Try not to avoid that because they don't always make circles and stuff. Okay? It can be a lot more complex than that. And that just makes your life hell if you try to deal with that. Okay. So can everybody see your link, twists, and width? Okay. Fantastic. Okay, this is actually that supercoiling happening. Here we have the supercoiling in effect, and here we have no supercoiling in effect. See, this is essentially the single circle. We don't have any other width in there. Okay, and so which one takes up more space and would be more difficult to move and deal with? This one with no supercoiling, right? Yeah. And so again, remember, the supercoiling is just like you if you're trying to store a hose, right? What do? You wind it up, don't you? You add supercoil to it, okay? When you want to use the hose or parts of the hose, what do? You have to uncoil it, don't you? And you can actually see some of that right here. See, there's portions of it that are starting to get untangled. Now, that happens on its own sometimes, but it also happens due to some specific proteins and enzymes that we're going to look at, okay? I don't know how much we're actually going to be able to get into that, but we'll get at least a pretty good basis. Now, the topology, this is the branch of mathematics that's going to deal with the structural properties that are unchanged by deformations. The linking number, LK, that's that same linking number from before. This is the number of times the strand of DNA winds in your right-handed direction around the helix axis when the axis lies in a plane. And again, that's looking at it from this direction right here. Okay? This is called right-handed twisting. Looking at it from going this to this. Okay? Have you guys done any of that in physics? Right-handed twisting versus left-handed twisting? Okay. Yeah, it's a big thing on electromagnetism. There's something called the right-handed rule.
Yes, I do remember that.
It's okay.
Yeah, it's so long.
It's okay. Anyways, right-handed direction. Take your right hand, point the thumb the direction, and then where your fingers are going. That's how it twists around. Okay. Okay. It's kind of interesting that it shows up everywhere all the fucking time. That's how electromagnetic fields work. Which, by the way, is how power is actually transmitted through a power line. It's not transmitted in the power line. It's transmitted through the electrical field. No, right? The power line just equilibrizes. Does blow everybody's minds? Yeah, it is kind of. So if you ever look at the distance and how fast a light could get turned on or how fast you can signal change, it's the speed of light of the electromagnetic field not passing through the power line. The molecules differing only in the linking number. These are going to be topological isomers, or topoisomers of each other. Okay? I know, it's a lot like organic chemistry, isn't it? We have another isomer. Woo! All right, so the twist, this is going to be a measure of the helical winding of your DNA strands around each other. The rib is going to be the measure of the coiling of the axis of the double helix, or the supercoiling. Really, for you guys, this basically amounts to the same thing, unless you really start getting into it. You can just remember this is like a very, very good definition for what you would consider supercoiling. Okay? The linking number, this is going to be the sum of the twist and rib. So if we take the twist plus the rib, this is always going to give us the linking number here. So most naturally occurring DNA molecules will be negatively supercoiled. This is due to the unwinding or underwinding of your DNA. So typically we would get negative supercoiling for basically the same reasons as we get negative supercoiling when we wind up a hose, right? So if you're winding it this way, which direction do you have to wind the hose to get it to stop supercoiling and kinking up on you? The opposite, right? Yeah. Topoisomerases, this is the enzyme that induces or eliminates supercoils. There's a couple topoisomerases that you have to understand. There's type 1, which is going to catalyze the thermodynamically favorable relaxation of supercoiled DNA. Basically, you've all taken some headphones or something with a wire or a charging wire and coiling it, and then you lift it off the ground to let it relax. Okay, kind of similar to that. We do it in kind of a weird way because, it's light, it's small. We're not necessarily going to be able to depend on gravity to do it, right? The type 2 topoisomerases is going to use free energy from the ATP hydrolysis. This is going to add negative supercoils to our DNA. This is more like you doing the hose and then physically taking your hand and unwinding that pressure. Okay? You're using energy to counteract it. Okay, so the topoisomerases is going to change your linking number in a 3-step reaction. Step 1 is going to be the cleavage of 1, and that's for type 1, or both strands, and that would be type 2. Now, they did a great job numbering this. I don't know if that's on purpose or they just got lucky. But type 1, you're going to cleave how many strands? 1. Type 2, you're going to cleave how many strands? 2. Isn't that beautiful? Yeah, you gotta appreciate those moments, right? Being in biology, there's so few of those moments. Okay, so again, cleave the strands. I know this is such a stupid way to do it if you think about the examples I gave you, right? But remember that, again, those are macro objects where you can depend on gravity to help you out, okay? Micro objects like this, there's other forces that are so much larger than gravity. So you can't depend on that. Step 2, the passage of your segment of DNA through this break. So we cut, pass through, okay? Step 3 is going to be the resealing of your DNA break. Cut, pass through, rejoin. Cut, pass through, rejoin. Okay? And that's going to be all of these. Now, the specific how it passes through is going to change a bit, because one of these cuts both strands, right? Meaning you can just pass through the whole damn coil, can't you? Okay? The other one only cuts one strand. Okay? The passing through is going to look a little different. So this is type 1 topoisomerases. This is going to be for relaxing your supercoiled structures. Again, type 1, how many of the strands do we cut? 1. Very good. Okay, so step 1 is going to be the DNA is going to bind inside of the topoisomerase cavity. The hydroxyl group of the tire 723 is going to attack the phosphoryl group on one strand of the DNA backbone. This is going to cleave the DNA, and it's going to release a free 5' hydroxyl group from that DNA. Step 2, the cleaved strand is going to rotate the remaining strand. This is going to unwind your supercoil in a controlled fashion. Think of this a bit like, what are those? Shit. I'm just blanking out. There's a toy where you wind the thing up and it has a little thing you pull, and then it allows it to start spinning. Does that make sense? I'm just not remembering. Yeah, they like oftentimes ballerina, or they can be, you know, whatever you want, princess. Yeah, yeah, and then you pull the deal. So it has 2 connections. It doesn't allow it to rotate, right? Just like if you were to form 2 connections, like a double bond or something, like I had you guys do last semester with double bonds. You can't rotate. But what happens if you remove 1 connection? You can freely rotate, can't you? And so you go from 2 connections to 1 connection so you can start rotating. Okay? And once you're able to freely rotate, that's going to unwind on its own, isn't it? Because there's going to be torsional energy from that supercoiling going on. Okay? Does that make sense? Okay. Probably have to come up with a new example. Everybody's seen rope when it frays and then breaks? You get the same thing, don't you? Like it suddenly goes whoosh and spins really fast because it has supercoiling. So the step 2, the unwinding happens. Again, this is going to happen in a controlled fashion, though, whereas the rope would be an uncontrolled fashion. And probably a prelude to something disastrous. This is going to be driven again by that release of the energy that's stored in the supercoiling. Step 3 is going to be the free hydroxyl group of your DNA. This is going to attack the phosphotyrosine residue. This is going to then reseal that backbone and release the tyrosine. Does that part make sense to you guys okay? So remember, you're twisted, and so it's higher energy structure, right? Kind of like my fingers are higher energy because I have them the wrong way. And then when you release them, they're going to reset, and you're going to be the more energetically favorable structure. And like many bonds that have a nice equilibrium, it will break apart and reform on its own. If you're the relaxed form, then nothing's going to happen when it breaks apart, right? If you're not relaxed and it has energy built up, it's going to unwind. Okay. This is actually a more the reaction, what you're looking at. And so, again, we're going to take this 3' end right here. We're going to attack that phosphodiester linkage right here on this end right here. This is going to release this side right here. Again, that's that 5' hydroxyl group right there. And that is then going to allow this to start unwinding. Okay? Because, again, this side will be free on one side of it, right? And only have a single bond. This is the topoisomerase 1 that's going to binding. It's actually binding right now, the DNA right there. Everybody okay with that? Ooh, so beautiful. Okay. Okay, everybody can see the DNA strands and everything? Okay, fantastic. Notice, by the way, there's the blue, red, and then we have the enzyme in orange. Okay. Okay. So this is a negatively supercoiled DNA, again, that we've inserted in here. And what's going to happen here is we're going to have equilibrium reactions on every step of the way. This one has equilibrium reactions because we're not powering it, right? So we can go back and forth at any time. What's actually powering this process? The coiling here, right? Okay, and so what we're going to have is, again, that's that Y right there, the tyrosine. It's going to bind to that 3' on the phospho right there. This is going to free the 5' end. Now we're only joined by one single bonded strand. And so this can now unwind. It's going to unwind 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. One of the supercoils, right? Okay. And we unwind And then again, we just have that normal equilibrium that's going to exist, where this could transfer onto this OH group, or it could be onto the other OH group. Okay? They're energetically fairly similar. Right? And so it's going to just have that normal equilibrium reaction going back to the other OH group, which is on the DNA strand in this case. And that rejoins, leaving us minus one supercoil. Okay? Can we go backwards with this? Oh, definitely. Yeah, if it becomes energetically more favorable for whatever reason, we'll end up going backwards, right? Or if it's just low enough energy, the energies of the supercoiling are similar enough, we'll be going backwards all the time. Forwards and backwards. Okay? Okay, so type 2, this is the topoisomerase type 2. This is going to introduce negative supercoils. This is going to be through the coupling to ATP hydrolysis. This is where we're winding it up more than it would normally be. Okay? So step 1 is going to be the enzyme binds one double helix. This is going to be termed the G segment. Step 2, each monomer of the enzyme is going to have a domain that will bind the ATP. It's going to lead to the conformational change that's going to bring the domains together. Step 3, the complex is going to bind a second double helix. This is termed the T segment. This is going to be leading to a conformational change that will trap the T segment. Step 4, the conformation change is going to force the separation and cleavage of both strands of your G segment. Step 5, the T segment is going to pass through the cleaved G segment. Literally cut, pass through. Okay? Step 6, ligation of your G segment. This is going to be leading to the release of your T segment, so you don't end up going backwards. Step 7, the ATP hydrolysis, again, release of the ATP and the orthophosphate. This will reset the enzyme with the G segment, still bound actually. Right here's the ATP sites up here. These right here is the DNA segment binding sites down here in this yellow. Okay. By the way, does that look like something? It actually kind of looks like a scissors, right? Okay. Funny enough, it kind of does work as an example of a scissors, though it doesn't actually work like a scissors, okay? Like the overall form, though, as it goes along. It's kind of scissor-like. So first we bond the first portion of the DNA strand, which is going to be the G segment. So we bind that here, and that's going to change our conformation. Now, what's going to happen next is we're going to actually get the ATPs bound and the T segment bound, okay? And so now we're ready to go. So what's going to happen next is we're actually going to get a SNP. Okay? So these come together, like so, kind of like scissors. Snip. And we're going to actually snip the two strands of the G segment. Now note that that leaves the T segment trapped on one side of it, right? So what happens with molecules that are just sitting around in solution? Do they just sit there? No, molecules diffuse, right? And that's a natural process of the universe. And so this is going to have no other options than to diffuse to the other side or stay where it was, right? So eventually it's going to diffuse to the other side. And that's going to transfer it from one side to the other of this first coil, the G segment. Now what's going to happen next is it's going to ligate together the G segment. It releases the T segment, and it releases its ATPs. And that right there is going to leave us in this form right here where it's still bound to the G segment. Now note that it could keep doing this, right? This actually is a cycle. We will be gaining one supercoil each time. Okay, so the topoisomerase inhibitors. Bacterial topoisomerase 2, which is the DNA gyrase. Gyrase meaning like gyrate, right? Circular winding motion. This is going to be the target of some antibiotics that are going to be used to treat the bacterial infections. Novobiosine blocks the binding of ATP to the DNA gyrase. Again, that's that type 2. Nalidixic acid and ciprofloxacin are going to interrupt the breakage and rejoining of DNA chains. Camptothecin, it's an anti-tumor agent. It's going to inhibit the human topoisomerase 1. This is going to be doing it by stabilizing the form of the enzyme that's covalently linked to your DNA. And so these are some examples of that, by the way. Here's nalidixic acid, that's this one right here. Ciprofloxacin, that's this one as well. So the DNA replication has to be highly coordinated. If we're trying to replicate wound DNA, is that going to work out really well? No? Do you, so you're trying to put in a new light, so you have wound up wire, and you cut the middle of the wound up wire and you try to hatch something into it? No, that's not going to work out, right? To replicate DNA, you actually have to do some unwinding, don't you? Okay? Because you have to expose that site you're going to be working on. So the DNA replication is very rapid. The E. coli genome, this consists of 4.6 million base pairs. This can be replicated in less than 40 minutes at a rate of 2,000 nucleotides per second. In the E. coli, the replication begins at a single site. In the eukaryotes, there's going to be multiple initiation sites. So replication polymerases are going to be characterized by their very high catalytic potency, fidelity, and processivity. Processivity is going to be the ability of an enzyme to catalyze many consecutive reactions without releasing its substrate, i.e. that it has high process order. Okay? Because remember, every time it releases and comes back on, that's diffusion controlled, that's going to slow down considerably, right? We haven't really seen that yet because we haven't seen processes where we can just run along a huge chain, right? Technically, I guess we could have seen that in glycogen, but not as much because we don't get that long chain without a branch. The source of the processivity in the E. coli, this is going to be the sliding clamp. That's the beta-2 subunit. That's going to be a dimer that forms a ring around the DNA duplex. The replicative polymerases are going to include subunits that assemblies that will function as clamp loaders. These are going to be by grasping the sliding clamp and using ATP to open and close the clamp. So this right here, this is the sliding clamp subunit of your DNA. This is the polymerase 3. It's a dimer. And you can see the two sides of the dimer right here. And you literally assemble the clamp around it. Just like you would for like clamping onto a rope. Anybody ever seen like the rock climbing clamps? Or use them? Okay. Did that make sense? Very similar, right? You even use energy to open and close it, don't you? So you climb along. Again, this is going to have enough space between the DNA and the polymerase to allow rapid sliding during the replication. If you change this amount of space, does anybody have any idea what would happen? If you made it really small, what would happen? Yeah. If you made it just a bit smaller, it would start getting stuck, right? It'd move slower. If you made it too small, you wouldn't be able to fit on in the first place. What if you made it too big? Yeah, you'd get torsionals, right? States, where it won't have everything binding properly. Okay, so the leading and lagging strands are going to be synthesized in a coordinated fashion. Replicative polymerases are going to synthesize the leading and lagging strands simultaneously at your replication fork. So the leading strand is going to be synthesized continuously. The lagging strand has to be synthesized discontinuously. Otherwise, you'd have to have an entire new setup, right? You couldn't replicate this setup. So the single-stranded binding protein, SSB, this can bind to the unwound strands to keep these strands separated. What would happen if you didn't have this? Which is energetically favorable? On-wound DNA or wound DNA? Single-stranded or double-stranded? Yeah, double-stranded. Because remember, it's still together on one side, isn't it? So it's actually energetically favorable to just come back together on the other side and leave a little gap for your unwound. So you actually have to have these binding or else they would actually come together constantly. And then you wouldn't be able to replicate the strands, right? The leading strand is going to be synthesized continuously by your DNA polymerase, and the topoisomerase 2 concurrently introduces the right-hand negative supercoils. I know, you thought it would just be like all the other classes where you got your DNA, boom, magic. We synthesize it off the leading and lagging strands, right? Nope, no such luck. This right here, this is again that replication fork. Can everybody see your fork? Fantastic. Here's your helicase. What is that doing? It's unwinding it. You got it. You have your 5' going to 3', and you have your 3' going to 5', right? Okay. All right. And we notice right here we got our red strand. Which one is that again? Yep, it's the leading strand, and that goes what direction? 5' and 3'. You got it. And so we're going to be synthesizing this new stuff from the 5', making the 3' every time, right? That's the one we're joining. And so this is your sliding clamp right here. This is your DNA polymerase over here. And so the sliding clamp's going to slide along. You can think of it as the second zipper, okay? So it's also making sure these are joined, by the way. If they weren't joined, the sliding clamp wouldn't be able to go along. Okay? And this right here is the DNA polymerase. This is actually joining together your new daughter, right? Okay. Over here, we actually have the SSB. What's that again? You got it. You got it. Yeah, that's the one that's going to keep this from just binding back on, right? It's also going to be the little pegs that let you know, hey, we need to do this for the lagging strand, okay? And that's because this machinery right here only goes along this direction, right? But we're actually freeing these the wrong direction, aren't we? We can't go down this way. We have to go down this way, okay? And so this is going to join. It's going to synthesize. We actually need to put an RNA primer, by the way, to start this process. And it's going to be synthesizing there. This, we don't see the RNA primer because we've been doing this for a while, right? This one has to start up all the time, doesn't it? Okay. Anyways, there's your lagging strand right there. So the DNA polymerase 3 hollow enzyme is going to include 2 copies of your polymerase core enzyme. This is going to consist of the DNA polymerase, that's the alpha subunit, the epsilon subunit, which is the 3' to 5' proofreading exonuclease, the omega, just called, you know, the funny part is I often hear this saying 0 strand. But anyways, yeah, Greek. The 2 copies of the dimeric beta subunit, this is going to be your sliding clamp. The core enzymes are going to be linked to a central structure that is this complicated mess right here. This is going to interact to the helicase. So the YT2 delta delta prime complex is actually the clamp loader. The chi and phi subunits are going to interact with your single-stranded DNA binding protein. And here's that whole thing together. Okay? I know, pretty complex setup, isn't it? Good stuff. All right, so remember that this is going to be that entire hollow enzyme complex, okay? Again, as the DNA polymerase hollow enzyme, and our multiple subunits. So right here we have the helicase, that's going to be the unwinding portion, right? Then we have the core right here and here. And these are going to be where we're going to actually have the clamp, and then we're going to have the polymerase. And then this is the body right here, which is the clamp loader and essentially the structure that this is going to be around. Okay? Everybody okay with that so far? Fantastic. All right, so let's talk about the synthesis of the lagging strand. The lagging strand is going to have to be looped so it passes through the polymerase active site in our 3' to 5' direction. This will allow the synthesis to occur in the 5' to 3' direction for the daughter. The DNA polymerase is going to release the loop after synthesizing approximately 1,000 nucleotides. This is going to be done by releasing the sliding clamp. And then we'll have to start that again and release. Start it again, release. Okay. The new loop is then going to be formed. The sliding clamp will be added. The primase is going to synthesize a short stretch of your RNA primer. Primase RNA primer. The one saving grace of this is everything means what it is named. Okay, so your DNA polymerase 1 is going to fill your gap between the fragments. It's going to remove your RNA primer. The DNA ligase is going to join the fragments to yield an intact strand. And we can see this process right here. This, by the way, is the trombone slide. Can everybody understand why that's called the trombone slide? Everybody's seen a trombone, right? And it goes out. Yeah. And it's going to come back in, right? We'll start again. Okay, so again, this is our lagging strand. Does anybody have any questions about that? Okay, this being that second part of the holoenzyme right here, right? Okay. You all have a great day. I will see you on Wednesday.